Hello, everybody. Today I'm going to briefly talk about our paper, Generative Patch Priors for Practical Compressive Image Recovery. This is joint work with Suhas Lohit from Mitsubishi Electric Research Labs and Pawan Turaga from Arizona State University, and I am Rushil Anirudh from Lawrence Livermore National Labs. In the paper, we study the notion of a generative image, a patch prior. This is different from a generative image prior or GAN priors as they have been sometimes called, which have been shown to be very successful for inverse problems. They essentially work by restricting the problem, the solution to the inverse problem, to the range space of a pre-trained generator. The GPP basically relaxes this idea by restricting not the entire image, but only individual patches of an image to the range space of a pre-trained generator. Since as a result, GPP can be used to represent any natural image using an appropriate patch composition function, as opposed to GAN priors, which are only applicable to the training distribution. As long as we know how to combine a set of patches into an image and decompose an image into a set of patches, we're able to use GPP. As an example, we show this image in the paper where we show the optimization process for GPP at a compressive sensing measurement rate of 10%. And we see that we're able to recover high quality detail even by relaxing the prior to the level of patches. Essentially, we represent every image as a batch of patches. So the larger the image and the different aspect ratios, they can all be just treated as a batch of patches. In order to achieve this for compressive sensing, we look specifically at the patch-based sensing regime, where given a measurement matrix phi and an unknown ground truth image that is sensed at a patch level independently. So to simulate this process, we break an image down into patches and sense every individual patch with the same measurement matrix. Here, we measure it at a measurement rate of 10%. We then use, to recover the image, we use a pre-trained patch GAN. In this case, is just simply a DC GAN trained on CFAR. Because CFAR images are of size 32 by 32, we treat our patches of size 32 by 32. So therefore, an image of 256 by 256, for example, can be broken up into non-overlapping patches, 64 non-overlapping patches. Using this pre-trained GAN, we make an initial guess of all the 64 patches. And because initially they're guessed at random, they're random patches. And then we sense each of these patches with the same measurement matrix and compute a loss. We compute gradients that minimize this loss and update the latent space so that our patches get more informed so as to estimate the ground truth. As the optimization progresses, we find that even imposing this cost at a patch level, the patches are able to converge to the solution with very high accuracy. Even with just 10% measurement rate, we're able to recover images with up to 24 to 25 dB, which is much higher than state-of-the-art methods. This is an entirely unsupervised method, which is broadly applicable. To compare it with other priors, we look at two axes along generalizability and efficiency, where on the generalizability scale, if a prior that is high up on that scale is applicable to any image and a prior that's low is applicable to only to specific image distributions. Efficiency is essentially the quality of the recovered image under very few observations. We know that classical priors like sparsity or total variation and more recent ones like the deep image prior are applicable to any kind of image, but they tend to be less efficient in the sense that they cannot recover a great quality image because they make very few assumptions about the data. Whereas a GAN prior that is trained on, let's say, only on faces is able to recover an extremely high quality reconstruction for very few observations, but does not generalize at all. GPP occupies a sweet spot where it's more efficient than classical priors, but way more generalizable than GAN priors, and as a result is much more practically applicable. In quantitative reconstructions, we observe that the GPP is significantly better than existing priors, both at a 10% measurement rate and much more so at a 1% measurement rate. We also study reconstructions on real compressive sensing datasets with uncalibrated measurements. We propose a variant of GPP called the self-calibrated GPP, which is able to automatically adjust for misalignments in the measurement matrix from hardware artifacts that can occur in the real world. We show that the self-calibrated GPP is able to improve on a lot of the baselines, including supervised methods, and performs on par with many of the manually calibrated experiments. We have many more experiments, ablation studies, and results in the paper. Please contact us if you have any more questions. Thank you very much.